Okay, it's 1:30, Friday afternoon, long weekend coming up, and I'm sure you're feeling good. So today we're going to be doing the last lecture on or presentation or on beam elements. Now, on Tuesday, uh, we're going to start a brand new topic. The beams are not going to go away, though, okay? They're going to come back later on. And there's going to be a homework, of course, which is going to be posted on YouTube with the solution this Saturday, probably. So watch it. There's going to be homework too. Lab 51, Lab 52, Lab 53, Lab 54. The problems are a little bit different, but as far as getting access to the PDF file, you're going to see it on the YouTube, but you can't get the PDF file until your lab starts. That's the way the GA set it up. So, so this next homework is going to be on beams. Okay. Now, before I start my final presentation on beams, are there any questions? Okay, I guess there are not. Let me quickly remind you what we did last time. We talked about beam elements. When you took your stress analysis course or deformable bodies course, when they talked about beams, all you did was to draw a line. You didn't say, you didn't show any three-dimensionality, etc., but the information was supplied in the form of cross-sectional shape and dimension, which translates into the mass moment of inertia or second moment of area, the I thingy, okay? Now, in the case of 3D beams that we are dealing with here, because the beams can be in 3D, that's not good enough, because you can draw a line and you can have a cross-section, for example, a rectangular shape like that, rectangular shape like that, or the same thing. The orientation of this cross-section also matter. The only time that it doesn't matter, the orientation doesn't matter, is when the beam has a circular cross-section. Okay, so the moral of the story is that you should be hoping that the problem that you get on a homework, on a test, has a, well, on a test, let's say, has a circular cross-section. Therefore, you don't have to worry about this one other aspect that needs to be concerned about. Now, today, I'm going to solve this problem for you. And then this may look familiar. Wait a minute. Okay. This may look familiar because the second or third day of classes, we did a C-clamp. Remember the C-clamp, which had a hole on the top? And we fixed the top of the surface of that hole, and then we took the other side, the other edge, the bottom edge, the bottom face actually, and pulled it down. Now, we're going to solve that problem, except that it is going to be done with beam element. There is nothing exotic about beam elements. Beam elements, you just draw it as, basically a line or a curve or something like that. You don't draw the three-dimensionality that you showed in the case of, for example, the solid elements, or that C-clamp that we did before. But there is a caveat. These beams are very versatile elements, but they do not provide you information on stresses. And I know that some of you might say, well, if it doesn't give me the stress, what good is that going to do me? You're absolutely right. You're absolutely right. If you want beams, detailed information about your beam, you can get it from Catia. You're right. But pretend that this beam, this frame, was used to connect an object up here to another object down there, or somehow this was the intermediary. You may not care about detailed stresses in the beam. You want to see how the load transfer, so that you can look at the stress distribution in the top part or the bottom part. All right. Now, right. Okay, I'm going to do this problem I'm going to do it two different ways. How about that? One is using the sketch. So I'm going to put this thing in a sketch. You know what a sketch is. and then proceed from that point on. And then I come back and solve and do it as a wireframe. Wireframe is not a sketch. It's a bunch of lines and curves and points and perhaps splines and things of that type in space. And you're going to solve it like that, which is more involved. However, sometimes you may not have a choice, okay? Because if your frame structure, such as this, cannot be put in a plane, then obviously you cannot have it as a sketch, because a sketch is a two-dimensional plane, okay? For example, if you took an actual spring, winding spring, which is used in a car, that is modeled with beams and can be modeled with beams, and that does not fit a plane. In a plane, it's a three-dimensional object. Okay. Once I solve that problem for you, I will come back and do a modified version of this. Now, what do I mean by modified version? This problem, clamped on the top, the bottom being pushed down, does not have any planes of symmetry as a beam element, okay? As solids, remember that we did have two planes of symmetry. Okay, well, we had one plane of symmetry for sure. We got one plane of symmetry, not two. Okay, but if we look at this other problem, modified problem, that the top is clamped, you can see that. Not here, though. If the top is also exerted to the same force and basically separating these two by applying force at the two ends, and if an observer is standing here and look at the left side and the right side, she's going to say there is no difference between the left and the right. If there was a clamp up here, she would say, oh, that one is clamped, this one is not, and I know that they're different, and she's right. Okay. However, for this problem, she's going to say, hey, there's no difference. Why should I do the whole thing? Because I know everything about the top. If I know everything about the top, I know everything about the bottom, and that is correct. So this being the case, you can say that in this problem, not the previous one though, in this problem, x, y is a plane of symmetry. In other words, I can model only the top or the bottom. You might say, okay, but what about y, z? Let me remind you, when we solved the C-clamp problem, exactly the same C-clamp problem, exactly the same, okay? Exactly the same C-clamp problem. I did this for you too. I said that YZ is also a plane of symmetry. YZ is a plane of symmetry, and XZ is a plane of symmetry for solid elements, for that bulky object that we created. And you're right. You're absolutely right. But let me put it this way. Have you ever tried to use a scissor to cut a rope? Well, it's very easy to cut a transverse to the rope. In other words, you hold the rope and you bring the scissor tongues in and just clip it. That's easy. Have you ever tried to cut a rope along the string? Well, in principle, it can be done, but you need an extremely sharp and microscopic microscopic scissor to do that. Okay, so do not split hair. Do not split beam element along the length. Can't be done. You don't do it. You can split it perpendicular like that, but not along. You can do it with solids. Okay, with solids, you just cut it or split it and then put surface slider there, etc. So we're going to come back and do problem. There is a few things that you have to worry about, and that is if you cut it in a solid with a solid object, you put this thing on a surface slider. But there is no surface here. There is no surface. So what do I do about this plane of symmetry? We'll do that later. Okay, if there are no questions, I'll give you a few seconds. If there are any questions, raise it, please. Otherwise, we move on. So let's start with our first problem. We're going to start with a new part file. New part file. There we are. And immediately we save it. Let me make this thing a little bit bigger. Okay. So on a convenient plane, on that vertical plane, I will sketch. Oh, so I'll immediately save it. Right, let's do that. File, save management, save as, desktop, new folder. I'm going to say lab, section 52, lab 52. Okay. I'm going to put it in here and give it a name that I can recognize. So I'm going to say your student ID number 123456789. Your last name, Bernoulli. Bernoulli. Yep. And identifier, homework. Not, it's not homework. Lab. I don't know, 52 underscore. I'm going to say beam, but with a sketch. How about that? Beam sketch, because I'm going to come back and do it with wireframe. And I want to be able to distinguish between these when I look at it and I go home. Okay, good. All right, let's make the shape of the beam. The only thing that we have to do is to draw this. And we're going to do it as a sketch. So on a convenient plane, on that vertical plane, I will sketch something that resembles that C. Okay. So let me see now. Where's this guy? I will draw something like that. Wrap it around. And then go. It makes it nice and symmetric. The top, control the bottom, control the middle, and we make it, symmetric. Yeah, good. Let's put some dimensions here. So this guy is 3. So is that one? 3. The radius of that circle is 1.5. 1.5. And exit. And there is my part, basically. Now, remember, we talked about this thing. Last time and today, and we said that in order, if you have a non-circular cross-section, and in this case it's a 1x1 square, that orientation point is important. Unless it's a circle, you don't have to worry about it. So let me create a point, which I'm going to be using for the orientation point, and I'm going to use 0, 0, 0 right there. If it's bothering, well, if you can't see it, I can even move it this way so that you can see it. But yeah, let me actually move it a little bit. So let me see why. Okay, just so that, too much. Maybe 4. Now, look, I know that some of you are going to be concerned that this is a wishy-washy description of this orientation point. Well, the thing is that, first of all, if it's circular, you don't have to worry about it. If it's non-circular, there is a process, there is an algorithm that Catia uses for you to tell you what that orientation point does. The orientation point, it drops a perpendicular to the curve, And this point right now is in that plane. So when you drop a perpendicular to that plane, it's going to be something like that, like this. This is the y direction. X is always along the beam, okay? And Z is perpendicular to 2. The moral of the story is that this XYZ that is talked about in orientation point is not this XYZ. X is along the beam, Z is the perpendicular, Y is the perpendicular to the beam, and of course, once you have X and Y, the cross product of the two will give you Z, okay? This point cannot be on that curve because you cannot drop a perpendicular, okay? It cannot be on the continuation of that curve because you cannot drop a perpendicular. It has to be off that curve. Okay. Now, the one thing that you do before you move any beam problem, you join it. There is join right there. And remember, join is not in part design. It is in generative shape design right there. This is not part design. This is generative shape design. If you want to get it, you go to File, You go to start, what is that? Not mechanical. Shape. Okay, generative shape design right there. Okay, but okay, I already there. So you select it. You join this sketch. Without joining it, you cannot do the rest of the problem. Okay, and apply material to it. Apply material on this part. Let's make it out of steel and say okay, and you're done. This is our part, nothing exotic. So file, save management. Or did I already did that, right? I already did. So all I have to do is to click on the floppy. I already did the preliminary work. Remember I called you Bernoulli? Okay, good. Now we're going to go to generative structure analysis. If you have not personalized your Catia interface, you go to analysis and simulation, generative structure analysis. So the first thing that you're going to do is to mesh this. Catia doesn't see any three-dimensional objects. Okay, it just kind of leaves it to you now. So the beam measure is right there. There, beam measure. You select this, turns yellow. I put a 0.3 here because remember that this length was 3. Now beams are very versatile, and very big beams can do an excellent job for transferring loads and things like that. The problem is that if I put too big here, for example, hypothetically, if I put, I don't know, 3, then there is no problem there. There's going to be one element here, one element there. But this is going to cause a problem. Sorry, this is going to cause a problem. You have to break this up into small elements. And if the element is big, basically you don't represent the geometry well. That's why I made it 0.3. Beams are very efficient. You can make it extremely small. Don't do that. Extremely small, and but it's not needed. Now, parabolic elements, I don't know why they have it there. It doesn't work. Okay, linear, no problem. Now you can look at your mesh if you want. Right click mesh visualization if you want. The mesh is already there. But if you want to see it, you want to show somebody, you want to look at it, it's nothing exotic here. You get zoom in. Here is element number 27, goes between node 4 and node 29. Here is element number, whatever it is, 28, goes between 29 and 30. Okay, good. So deactivate this, deactivate that guy. All right. Now let's do the cross section. 1D property. I mean, you don't have to be. This is a no-brainer. 3D property is for solid object. 2D property for shell that we're going to start next week. And 1D element, it looks like an I-beam, right? Click on it. I already did this problem twice today, so I already changed that. It is a rectangular beam, not a circular one, rectangular one. Click on the wrench. I put the correct Y and Z, 1 and 1. And let me remind you, let me say OK, and select your support. There's the support. You see that? Support. There's your thing. So what it does, it puts it in a haphazard way. Now, if you want to straighten this up so that it's exactly what you want, you need the orientation point. So no, you can't even close this. If you don't select an orientation point, you can't even close this. So orientation point, and I'm going to select this and watch what happened to the red stuff. When I select this, it's going to turn them around and put them in order. Look, this is the way you wanted it, isn't it? This was the way the C-clamp was. C-clamp was like this. Okay, good. Now let's go and save an analysis file before we regret it later on. File, save management. There is the analysis file. Save as. In that folder, it's so easy to screw these up. It was lab 52. That is lab 52. And I'm going to use that same name here so that you can associate these with each other. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's your student ID. Your name is Bernoulli. The problem that we are doing is lab 52. I should have called it problem 1. How about that? Lab 52. That's okay. Lab 52. See, these don't have to match. It's just that it must be something that you can recognize later on what they are. It's a beam, and I'm using sketch. Okay, that's it's fine. and OK. Very good. Now this bottom is clamped, so I'm going to use the clamp icon. Select this. Oh, sorry, the top is clamped right there. Okay. Then I want to push this point down by 0.01 inch. Now in Catia, when you want to specify non-zero value for displacement, first you have to make it 0, and then you can change it. So you go to user define restraint. You select this point, and in the direction Z. This is not displacement. This is displacement. Z direction. You can see that right there. These are rotation. These are important. We'll see. Not in solids. Not important in solids. And we can change it now. Where is that thingy here? Enforce displacement. Enforce displacement. You select that guy, and you put 0.01. If you're pushing it down, minus 0.01. Minus. Say OK. You save it, and you run it. A couple of comments here, and I've said these things many, many times, but I'll say it again. Notice that the C-clamp problem that we solved was a three-dimensional object. It had a hole up there, and the hole was clamped. Well, you can't do details like that on beams. Beams is basically ignoring the hole and saying, you know, this is it. Now, the other thing is that here, when we did the solid problem, we said that the face is shifted down by 0.01. Here, we don't have the luxury of saying the face. We have to, if the face is basically represented by that single point. So we're going to say we apply a downward displacement to that point. The other thing is, in solids, you could get stresses. You can't get it in beams. That's why it was able to show us that this is the critical area of the beam. Well, we're not going to get that information here. We still know it's true, but we're not going to get it out of our finite element analysis. However, if this, as I said, if this frame was used to connect two parts together, although I don't know the stress here, I'm hoping that that is not my concern. I'm hoping that the failure is not in the beam, okay, in the beam, and then it will give you the correct deflection and everything. And because it gives you the correct deflection, it gives you the correct stresses for the rest of the structure, which is down here, etc. Okay. The moral of the story is that if you were working in the department who was responsible for designing this beam, then you would like to know what the stresses are, etc. You don't use beam elements. Okay. Run it. Where is this? Run it. I did run it, I think. Did I run it? Yeah, I did run it. That's why I get a displacement right there. Okay, so there we are. This is what you expect. If you animate it, it's exactly what you expect right there. You apply a downward force, etc. We don't know what the force is. You can ask Catia to do it, but down here, okay. If you want to look at the displacement, there's the displacement, the actual values. There is a displacement, average ISO. Instead of arrows, it gives you in this form, which some people may prefer. And notice that it not only goes down, it also goes to the left. Because that's why this is not symmetric. You can see that. This is why it's not symmetric. Okay. All right. If you want to get the stress, you're out of luck. This is dimmed. You can get axial stress that's totally useless. Okay, so are there any questions? Okay, do you want to know what the force is? Put the cursor. You have done this many times or several times together. Sensor, right click, create resultant sensor, reaction sensor. It says, where is your restraint? You can either select clamp or the thing that you use to push this thing down. Either way. So you use it to push it down. Okay, so you can select that. Or you can select the clamp. It'll be the same number. Update. And you have 255 pounds of force needed to do this. That's what, I mean, remember, this is a piece of steel with those dimensions that are given. And I'm asking you to separate these by 0.01. You need a substantial amount of force to do that. Okay, any questions? I guess the answer is no. All right, so we kill this. Okay. Now, I'm going to change this part on a different name because right now it says a sketch. Do it as a sketch, right? I'm going to change it to wireframe. So, okay. Where is that? File, save management. There is the part that is open and it has this name. I'm going to say save as. I'm going to change the name. Instead of being the sketch, we'll change it to wireframe. Wireframe, and then say okay. And I can ruin this whole thing. It's not going to affect my first calculations. Okay, so what we're going to do is the following. First of all, this join, I can leave it here. I can, you know, I can, let me delete it. Let me delete it. Just delete it. At this point, I'm going to leave it here because that's my orientation point. You can delete it, but then you have to create something for orientation point again. I'm going to delete the sketch because we decided not to do this thing with a sketch. So what is the strategy for making this thing? Well, the strategy is to create 5 points like that. 1, 2, 3, 4, 5. You know the dimensions and everything. 5 points in space, make a line, make a line, make a circle. This is not a sketch. This is a wireframe. So let's go ahead and do that. I know what these points are, so I know the coordinates of the. I've done it 3 times today earlier. So let's do that. Let me start with the top one. The top one is, okay, so let me see. The top one has a height of 1.5. 1.5. And for Z, I don't know, I use 3. Yeah. That's the first. Oh, this was the orientation one. Good. So that's the first one. Then another one is going to be over there immediately above this origin, which means your y is going to be 0. There we are. And then we have at the apex of that circle on the left. So z is 0 and y is negative 1.5. The radius of the circle is 1.5, right? There we are. And then down below, which means this is going to be 0 and minus 1.5. And then finally, that point over there. What happened here? Where are these other points? Let me see. Did I screw it up? I might have. 3. Let's check it. Let's check it. Okay, cancel that. Let me see how many points I've got. Okay, so this one was the orientation point. You know what? I somehow, maybe I pressed the, I don't know, I pressed the cancel. I'm not sure, but I'm too lazy to go and do a coordinate here. So I want to mirror this thing. Can I do that? Where's the mirror thing? Where's the mirror thing? The must be something here. Mirror. It's not worth it. Let me go and make it. We've got to look for that. Okay, so this one is going to be Z of 1.5 up. Okay, there. And this other one also I didn't do. So this one is going to be on that side. So Y of negative 1.5. 1.5. Z of 0 and X of 0. Yeah, right there. I don't know what I did. So right now there should be 6, 1, 2, 3, 4, 5, and the first one was the orientation point right there. Okay, fine. Let's go ahead and do the lines. So point to point, this is going to be the top line. Then it's going to be another one, the bottom line right there. Okay, and then cancel. I'm done with my lines, and I'm going to make a circle. There's a circle. The method that I'm going to use is 3 points. 3 points, whatever is convenient for you. This is very convenient. So 1 point there, 1 point there, and 1 point here. And the support is going to be the vertical plane, which is YZ. Good. Okay, very good. Join it. Now there's going to be 3 of them. It's just like a sketch. There was only a single sketch, so that's it. But here you have 3 curves, 2 lines and a circle. You can see that. Now you have joined it, okay? And material is still steel, no problem here. And we're going to click on the floppy because we already changed the name and everything. Now we're going to go to generative structure analysis. Everything is the same. All the steps are identical. So we say okay. Now mesh it. There we are. Same size element. The cross-sectional area, 1D property. You select the sketch. There's no sketch here. You select this guy. Any piece of it you select, it's going to take the whole thing. And notice that we can close it. Orientation point was this. And watch that he turned it so that everything is nice and oriented the way we want it. Okay. Now this point is clamped. There's 41 of you who are sitting there. I don't know how many of you are awake, but anyway, do not put it on this point. If you put the clamp here, notice that a point is picked, and when you run it, Catia doesn't see it, not on the point. What you do is you hide the point and put it on this vertex. There's a difference. The same thing down here because we're going to apply some kind of load on it. Hide. So clamp this thingy, which is not a point. It says it's a vertex. And then we push this thingy down. First we make it 0. There we are. And then we can change it. Where is it? Right there. We change it. By 0.01. Oh, very good. And save it. Remember, we have to save. File, save management. The analysis is not saved with the proper name. Save as. It's the same as the name before, except that this is wireframe. Because I already have something called sketch analysis, but this one is going to be wireframe. You can save that to, you can use that to your advantage instead of typing the whole thing. Wireframe. And say OK, and then say OK, and run it. Obviously, it's going to be exactly the same results. Well, I mean, nothing is exact in general, but when you use computers, but that's very similar to that. So you can see the deflection, the amount of deflection, I think it was 0.019. This is okay. Everything is the same. You can find the restraint, not the restraint. You can find the total force needed, etc., etc.
Excuse me.
Yes, yes.
So if we clamp the point when it's visible, would
Yep.
just that point be clamped instead of the whole sketch? Is that why we shouldn't do it?
Okay, let me change that to the point for you and show you that it will move as a rigid body. Okay, so let me go ahead. Let me go ahead to my static. There is the clamp. I'm going to delete this. Actually, I don't have to delete it. I'll keep it like this. First of all, deactivate the plot. Okay, deactivate the plot. Okay, good. So if you double click on the clamp, it's on the vertex. So let me see, remove all support and put it on that point. Let me bring that point into the view mode so that you can see. So let me put it so that you can see it. That was 0.6, I think. I think it was 0.5 or 6. I want to show it to you, okay? It was one of these. Is this the one? No, that was the bottom one. I then show there. Okay, right there. Okay, so let me put it on that point, not on the vertex. See, one point, and say okay. Agree? Agree?
Yes, Professor.
Okay, let's run it now. It will bomb out.
Okay.
Yeah, it'll bomb out. Sometimes it may run too because this is saying something else. When updating entity, no mesh. Yeah, because see, it says, hey, point. You put something on a point. Point is not, for example, a finite element mesh. It doesn't belong to a mesh. Okay. Sometimes it may even run, but it will fly away because it didn't see the restraint.
Okay.
All right.
Okay. Thank you, Professor.
Okay. You're welcome. Are there any other questions before I go and do this important thingy, which is symmetry in beams? We got time for a question. Are we good? Okay. All right. So let's go ahead and what am I doing here? Okay, let's go ahead here. I'm done with this guy. Now remember, it's asking me, should I change the last thing that I did? Remember, I made some stuff here. I take it to the point and then put the load on put the clamp on the point. It's asking me, should I change this? The answer is no. Don't change that stuff. Okay. So let me get not my wireframe, although I can work with the wireframe. Let me kill this one too. Let me get the one that was for sketch. Not that it matters. You can do it with this. So file, the one with the sketch right here. The part right there. Okay. Now I'm going to save it with a different name because I don't want to ruin the stuff that I did. So file, save management, this thing, save as, same name, except at the end, I will put down symmetry use. How about that? Symmetry use. Just be aware of the fact that the problem that I'm going to do for you is not the original problem, because the original problem had no symmetry. Okay, just be aware of the fact that when I say I'm just using a geometry of that, I'm not saying that this was symmetric. Okay, all right, good. Now we go here, and in our sketch, double click on it. Okay, I don't need this piece. This goes because I take half of it, right? And this guy, I take half of it. And one way of doing that is using the break to break it, to break this curve at that with that axis, for example. Where's the break here? Is this a break? No, this is a trim, not the trim. The next one is the break. I'm going to break this circle with that axis. Notice that it broke it up into two pieces. I can delete either one of them. I'm going to delete this guy. Do it any way you want. Okay, I had to get this geometry, and I did. And exit. And floppy, save it. Good, good. Now I'm going to go to generative structure analysis. Okay, we mesh it right there. Same size element, linear. We apply properties, 1D property on this. Everything is the same except the orientation point is also the same. It's just that it has to be taken. See that? That's the way you wanted it, right? Assuming that's the shape of our C clamp, like that. Very good. Okay. Now, first of all, we know what to do with this point. We have to push it up by 0.01. So first we push it up by 0, and then we change the 0 to 0.01. So where's that enforced displacement? Right there, there, and plus 0.01 because I'm pushing it up. If I had taken the bottom piece, it would have been going down. Now, it is a good idea that when you do these restraints, you say what they are. It doesn't matter to me. It's just that when there are 6 of these, you have no clue what they are. Look at the tree. But if you double click on it and put the meaningful name, so this is for the push up, so that you know this was used for pushing it up. Very good. Excellent. Now, this point is in the xy plane, and it's a plane of symmetry. Let me ask you a question. If you were doing solid elements and we had cut it, what would we have done at that cut? If it was a solid object and we were cutting it, splitting it, and we can't leave it alone, what would the name be? What would the name be? The name of the thing that we're going to use there? Can you say it, please? Can you say it?
Would it be a slider?
Slider, surface slider. Yes, yes. Now, the problem with the beam is that, wait a minute, I don't have a surface. Even if you try to use the surface slider, you won't be able to pick anything. Look, nothing. Surface slider looks for a surface, you can't find it. When it comes to beam, you have to do it yourself. You see this user defined? There's a very simple rule. Very simple rule. Let me unclear all of these. Let me remind you that even if it was a solid object, even if this was a solid object, and you created a cut here, and you put a surface slider, all that means is that the stuff in that cut that you made do not go up or down. This woman, when it looks at that point, you see that doesn't go up, doesn't go down. So a surface slider or a roller is nothing fancy. It's just that it specifies the displacement in the normal direction to be 0. So if that is the case, when we go here and we are saying that, hey, this is in the plane of symmetry, that woman looks at this point, it says it doesn't go up or down. No displacement in Z. So if XY is a plane of symmetry, no displacement in Z. This is the rule. If XY is plane of symmetry, no displacement in Z. If XZ is a plane of symmetry, no displacement in Y. Always perpendicular to that. But in beams, you have to do also stuff for rotation. If you can see the displacement, rotation is exactly the opposite. When this guy is checked, you leave that guy free. When these are not checked, you check them out. That is the rule. Of course, it's this point that I'm taking. So this is the symmetry. This is for use of symmetry or symmetry. Symmetry. Very good. Now, let me take you to last week when we solved this problem. We used solid element. We used solid elements like that. We made a cut here. Remember that? We made a cut through YZ, which we can't do it for beam. You can't split a hair. You can't split hair with YZ. You can't do it. We did it with XY, just like we did it in the solid elements. But when we did that, go back to the video, you see that even then this starts to move, because remember, the bottom of this piece was on roller. And you give it a kick, it starts moving. Nothing stops it. So what we did then, we fixed one point and said, you cannot move in the direction X, okay? Or the direction in the direction X and the direction Y, okay? When we did this problem, we did not have to say direction X. We did not have to say direction X because direction X was restricted because of the YZ plane of symmetry. But the moral of the story is here. You go there. This point can actually move in the direction X. Nothing stops it. Nothing stops it. All I said here was don't go in the direction Z. That's all. Nothing stops it. So we have to say don't go in the direction Z and don't go in the direction X. I can do it here, but I don't want to mix this up because you're going to come back tomorrow and say, what the heck? Symmetry. What are those? Why are those things checked? So I'm going to do another one. It says prevent rigid body motion. Uncheck that. I say prevent rigid body motion. Okay. And cannot move, that point cannot move in the direction X or direction Y. And which point is it? Let me hide this so that I can easily select it. That was symmetry, right? Let me hide this. This point cannot move in the directions X and Y because otherwise this can start moving that way. We can start moving this way. Nothing stops it. Before, we may have had surface sliders which prevented that, but not here. Now, it looks like it's all good. Not quite. Let's run it and you see what happens. There's something else that we have to do. We'll see. We'll see. We did most of the work. Most of the work is correct. But as you can see, not the whole thing. If you look at the display, this deformation, you will know and animate it. You see that, where's that animation? You see that whatever we did not take away the rigid body rotation about the z-axis, and that's what's happening. But if you look at the view from the top, for example, top, where's the top? If you look at this thing from the top, you can see it is spinning about that pivot point in the z direction. Now, we should take that away. We should take that away. So what we're going to do, we're going to say, okay, let's do another user define. I'm going to give it name, and the name is take away rotation. Take away rotation. Take away spin. How about that? Spin, rotation. And do not let it rotate about the z-axis and this point. Okay, so you can, if it's bothering you, you can take it, select it, hide that, select it. And I could have done it in the previous dialog boxes, but I don't want to mix these up, because if I put them all in those dialog boxes, tomorrow I come back, I don't know what I've done. Okay, and let's run it now. This time it will run, and I say a couple of more words before we quit. Done. See, it's done. So let me change my scale, by the way. Where is the scale? See, if I say show me the deformation, I can't see anything, because the scale was, oh, it's right here. I have good news for you for this, losing these guys. Okay, so yeah, I mean, notice that it did run. It gives you the same kind of thing. The numbers are not going to be the same that we got before, because we are solving a different problem. The other problem at this point was clamp. Now, those of you who are a bit more curious, if you look at what I did, you notice that this point actually ended up being clamped. Because go back and check all of these. These are the ones. You notice that all degrees of freedom are fixed. And you're absolutely right. In other words, if you started on this problem and I'm going to clamp that point, you are lucky, because you have done something that is correct. There's a difference between being lucky and understand why it's a clamp. But we give you full mark. We don't expect you to do it like that. If this was a problem on the test and somebody, instead of any of these things, they just clamped that point, you're going to get part marks. But if that was not correct, you have the opportunity of losing part marks from these things. Okay. But anyway, so that's it. Now, let me see. I wanted to say a couple more words about this. So as far as the beams go, we have a homework. It's going to be on YouTube. It's going to be posted on YouTube. You're going to do it. Give it to us next week. But and the beams are going to come back later on, because once I do shells for you, then we're going to say, okay, what about this problem which has something that looks like a beam behavior, something that's like a pop can, and something that is attached, a weld attached to some other piece, bulky object. So you have to use all of them at the same time. It is rarely the case that a particular problem is solved with only one type of element, all solid or all beam or all shell, as you see. And those are going to come. It's the last topic before the last week before the midterm. All right, folks, any questions? Any questions? Okay, so I'm going to stop the, wait a minute, what class is this? This is a lab, right? Yeah. So here's what I'm going to do. Listen, what I'm going to do is I'm going to stop this recording and kill this session. Kill the session. Start a new session, and that new session, I will call it lab. How about lab 50? I'll call it Friday afternoon lab. How about that? So I'm going to be here for you for the next 2 hours. and there are some GAs there too. But I will kill this because I noticed that when I have several different sessions created and run at the same time, sometimes people can't hear me from the other end, etc. So I will kill this session, create a new one called Friday afternoon, and I'm not going to record it. I'm just going to sit here for you to ask any question from me or the GA if you have any. Okay? So bye. I'll be seeing you in a few minutes. Where is this? Let's get through this.